So last time we started the new chapter, which is Anderson localization problem. And today we will continue trying to derive the expression for self-energy of electron, this scattered by this randomly distributed this impurities or this defects. So let me just remind you this system again. So consider a piece of metal and remove some of the atoms randomly, and then these electrons can actually get scattered by those impurity potentials, or where this those defect sites, there is effectively very sharp potential barrier where this electron cannot easily just go there, and then this electron can actually get scattered very easily very strongly by this delta potential. So we will derive such a Hamiltonian in just a moment. So the Hamiltonian for this impurity scattered in a many electron system is given by this H0 plus this U term. Remember, this U represents the sum of all this random potential, which I call this V as function of little ri minus this capital RL, where this capital RL represents this location of the site, or this impurity site. And this little ri represents this electron at any given site. So suppose there's no such a potential, suppose U is 0, then we could very easily see all this any electron wave functions for this unperturbed Hamiltonian is simply given by the Slater determinant of the plane wave solutions, meaning this eigenfunction, your P, is nothing but this plane wave e to the ip dot x, where x is just position of this electron. And this is simply just Fermi gas, right? Of course, we need to normalize this electron wave function by this box. And so we could simply just second quantize this Hamiltonian, and this H0 is simply just sum of a P, epsilon P, C dagger P, CP, right? But of course, you can imagine that the presence of this impurity scattering center located randomly in this material could actually be the source of this interaction. So the interaction is single particle scattering. This U term is actually single particle scattering. So in the background of H0, meaning we consider this U as a small perturbation. Okay? It's a local perturbation. So then the electron gets scattered by this very strong localized impurity at this given site. So the matrix element of this U between these two electron states, one is the incoming state, another is the outgoing state, is given by this matrix element. So suppose this is, say, initial state, and this is final state. And this is the side where you have this delta potential. And both P and P prime are just plane wave solutions of H0. This is what we assume. Suppose the impurity concentration is really, really low. Okay, suppose there's only a handful of impurities out of this many atoms on the lattice. So mostly these electrons on the other part of this system are described by this plane wave. Okay, but from time to time, this plane wave electrons will get scattered by this delta potential. So this is the picture of this Hamiltonian of this disordered metal.
Yeah. I think according to your model Hamiltonian, it's more like electron gas, and in this system put some impurity, right?
That's
because
right.
If a crystal, we need to use a block wave function.
Yeah, of course. Well, but I think this is, well, you could actually put this block wave function here. But I think the essence, the key physics is actually the same if you simply just assume that this is electron gas, right? Because you could consider this, the metal is just a free electron gas, more or less, right? Okay, of course it's a periodic potential, but if you consider just electron transport, for example, so this kind of a block wave function, you could, of course, impose this block periodicity here, but it doesn't change the key physics here. So that's why for simplicity, you could simply just consider a plane wave electron. This is the simplest possible towing model, okay, you can imagine, right? Of course, this is a bit naive, but I think this captures the main physics. Good. So let's just consider this matrix element of U in between this incoming and outgoing free electron states, and this is given by volume integral, right? Okay, by quantum mechanics. This is just the overlap integral of this expression value of this U operator, and this U operator is given by this sum over all possible this impurity of potential, little v here. Okay, so you sum over all the sites and all the spatial degrees of freedom, you get this piece of the matrix element. And we call this V in momentum space, because this is just like a Fourier transformation, because you consider a plane wave solution as the electron wave function, and if you insert this plane wave right here, and this is simply a Fourier transform of V of R, right? So let me just write it down explicitly right here. So V of Q is defined as this P prime minus P, which is a momentum transfer, which is this volume integral. Okay, so then we could just put these pieces together. As I mentioned, we could Fourier decompose the scattering potential like this. Okay, so later when we study this transport properties, we will again try to calculate sigma, right, self-energy in momentum and frequency space, right? So then we need to Fourier transform this scattering potential V of R to this V of Q. Okay, so this V is actually a real function. As a result, V of Q star is actually the same as V of minus Q. Okay, you can very easily see from the Fourier transformation of the V of R to V of Q, or vice versa. So this V describes the potential on the defect. So of course the potential is a real function of R. As a result, if you take the Fourier transformation of V of R to V of Q, and you take this complex conjugation of V of Q, you get V of minus Q. So simply because V of R is a real function of R. So let's just put things together. So if you have just many electrons, and capital N refers to the total number of sites, and you could describe such a scattering. So this potential term involves single particle or single electron scattering, as I mentioned, where you have an incoming electron and hit this potential, and then it gets scattered. And so we need to have this scattering potential term U of Q, which is a function of V of Q, right? And also this electron operator or density operator, C dagger P plus Q, and Cp represent this this incoming electron state, and P prime is actually P plus Q is the outgoing electron state, and then you sum over all possible P. And this rho I is actually the Fourier transformation of this delta, sum over L, delta R minus capital RL. So when you Fourier transform this total Hamiltonian, you need to sum over both I and L, as I mentioned here. Okay? So when you sum over L of this Fourier coefficient, and you will get this effective density of this electron on the side I, which is nothing but this electron density or this impurity density. All right, so let's just start from this Hamiltonian and we start doing perturbation. And let's take a short break.
What is the capital N?
Capital N is number of electrons. Okay, so you suppose that you have many electrons, right? And it may be surround this nuclear core at any site, and you sum over all such electron number.
A little bit confused. In general, second quantization form, for kinetic term, we need a capital N.
Well, you could imagine that, of course, this is sort of a non-standard. Okay, so this is just kinetic energy term around each site, and then you have a homogeneous distribution of these electrons, and as a result, effectively, you simply just multiply this by n, capital N. Of course, in the standard Fermi gas, we simply just sum over all possible momentum, right? But here, well, we could also do that, right? So we could also use the standard definition, but this is another way of representing the same thing. Okay, so we focus on this local electron kinetic energy, and then we multiply this by n, capital N. Let's take a short break. Okay, so in the following, we may just take the standard kinetic energy of the free electron by removing this capital N from this prefactor. So remember, we have to average over the disorder or this impurity distribution, and we assume that there is a distribution function or a probability distribution of those impurity or scattering centers. And a very naive assumption is so-called white noise distribution, meaning you have some kind of a uniform distribution of this probability, or you have an equal probability finding this impurity everywhere in the lattice. Okay, of course they are random. Okay, but there's no preference that this impurity could be found at any particular site. Equally probable. Okay, so as a result, you get this 1 over this volume factor as this white noise distribution. So when you average over this quantity sigma, which is the conductivity of your disordered metal, and you average over this impurity distribution. And so we just plug in this very naive white noise distribution. Remember, there the capital RL represents this position of this impurity or this disorder potential, and you calculate this sigma or conductivity of the system for particular configurations of this random potential, and you assume this is a white noise distribution. You sum over all possible the impurity position, and you integrate over such a capital RL, and you divide it by this volume factor, and this is so-called impurity average of your sigma. And remember, this Hamiltonian is given by this kinetic energy plus this potential term, and this little I refers to the electron position on site I, and capital RL represents the impurity. So you sum over all electron and also impurity. So then we consider this U term, this potential term, as a small perturbation. And as I mentioned, this term in second quantized form is this. Okay? So remember, this rho I at momentum Q is actually impurity density, which is the Fourier transformation of this delta function. Okay, so when you sum over all this delta factor, which is the location of this impurity scatterer, and this gives you the number which is proportional to the impurity number, and you divide it by this volume, so this is the impurity density, rho I of Q. Of course, this is at finite momentum transfer Q. Okay, so, but remember, in general, this rho I of Q is this summation, which is this integral over this impurity potential, or this delta function, which is the represent this location of the impurity in real space. Okay, and suppose you consider an average of this impurity density when Q equals 0, which means that you simply sum over all this number of impurity, and this is your average, your total impurity concentration. And as I mentioned, we consider a very short-range potential, which is a delta potential. So, and then this V of Q is simply just a constant. So let me define my potential. This is, of course, approximation. We consider extremely short-ranged potential, where this V of R is just delta function. And you can Fourier transform this general V of R in momentum space, and you'll find that in such a delta potential, this Vp is nothing but constant. V0 if V of R is just a delta potential. So meaning the Fourier transform this potential V of P is just a constant if we consider a very short-ranged delta potential like this. And this kind of assumption greatly simplify this mathematics and also give you a physically reasonable result. So let me just summarize what we have. So we have a Hamiltonian of non-interacting electron gas plus this very short-ranged random impurity potential, which is very short-ranged delta-like potential. And then when we calculate transport, we need to calculate conductivity, and we take the impurity average, and we make as simple as possible assumption, which is a white noise distribution, where this impurity could be anywhere with the equal probability. And you simply just sum over all possible configurations of such an impurity and then divide by this volume. Okay, so in following, we start from here and then we start to do perturbation. And the goal is to find sigma, remember, but sigma, as I mentioned, is actually a function of the current correlation function, right? And the current correlation function is related to the single electron Green's function. As we'll see later, you'll find that this is a function of single electron Green's function. The single electron Green's function, capital G inverse, is unperturbed single electron Green's function G0 inverse minus sigma. And this is something that we need to calculate. Sigma omega and sigma k omega could be computed within this very simple naive Hamiltonian Anderson disordered metal. And the only thing that we need to consider is the impurity average. So average over this impurity or disorder with a white noise assumption, and this is the thing that we need to consider in the following. So let's take a short break. Okay, so let's look at this interaction piece of the Hamiltonian, which shows this Fourier form, and it has this V of Q, which is a constant delta potential approximation. And this rho I of Q represents impurity density, and this CK dagger K plus QCK represents this electron scattering by this potential. So this will be a constant, but this is what we need to care about, because this is sum over L e to the I Q dot RL, right? It's the volume. And this rho I of Q represents this impurity density. So we need to take the average over all possible configurations of such impurity in your system, and then you take the white noise distribution as your assumption, and we need to really focus on this average of this rho I, and this V0 is just a constant. So consider this Feynman diagram, this perturbative expansion of the interaction, and the interaction vortex has this very simple diagram like this. As I mentioned, single electron come in and it gets scattered by this randomly distributed impurity potential, and this strength of this potential is given by V of Q times rho I of Q, where the V of Q is just a prefactor in front of the delta potential, and rho I of Q represents impurity density. And the momentum transfer between this incoming and outgoing electron states is given by Q. But remember, this is just a particular impurity configuration, and we need to sum over all possible impurity configuration and take the average. But we start from this diagram, and we consider the full Green's function as a Dyson type equation made of this basic unit of this impurity scattering diagram like this. So this is the simplest possible you can imagine of the interaction, many-body interactions, which is simply just a single electron scattering by a random potential. Okay, so this is this interaction vortex, so you need to simply just repeat this single diagram again and again in this connected way, right? But we haven't done any impurity average yet. If I simply just draw these diagrams, we need to take impurity average. So in this Fourier space GK I omega n, you could simply just use our notation. This is K omega n, and this is K omega n, and V of 0, rho I of 0. Of course, Q could be 0 or non-zero. So the first possible diagram is that momentum transfer is 0. There's no momentum transfer. This is simply just incoming electron carry the same momentum as outgoing electron and then exchange no momentum. And later we'll see that this diagram only shifts this chemical potential of the system, and we can ignore such a contribution. But the finite Q diagram is the thing that we need to consider. So this is Q and minus Q. V Q rho I of Q, V of minus Q, rho I minus Q. All right, so the first order term in the Fourier space can only give you this Q equals 0 diagram. Well, we will see that in just a moment. But the second order diagram will give you finite momentum transfer contributions, that the incoming electron carry momentum K, and then it gets scattered first by this impurity potential once, and then intermediate state or internal state of electron carry K plus Q and omega m, and then outgoing state carry momentum K again. But the second scattering processes actually give you a momentum transfer plus Q. The first one is minus Q. So then you get conservation of momentum if you consider this as a second order contributions. And the matrix of the interaction strengths for these two different scattering processes differ by a minus sign. V of minus Q, rho I minus Q here, and then plus Q on the other side. No, it's correct, because this is K, and this is minus Q, and this should be K plus Q. Because you need to sum over the incoming states and outgoing state. Okay, so this is incoming, and the other two is outgoing. So the outgoing electron states or outgoing particles carry total momentum K plus Q minus Q, which is same as K. So this is K plus Q. So let's just take a impurity average. So the first order correction, we need to perform this impurity average of this single impurity density term rho I of Q. So if we do this based on what we assumed, this white noise distribution, it is given by this average over L of this exponential factor, right? It's e to the minus iq dot capital RL. And you simply just plug in this white noise distribution, which is this multiple integral of the capital RI, where I runs from 1 to L, and L from 1 to actually NI, e to the minus iq dot capital RL, which is NI delta Q0, where capital NI refers to the number of sites. So you can very clearly see this result, which is the Kronecker delta function of Q and 0, which means that this is 0 if Q is non-zero, and this is 1 times capital NI if Q is 0. So this explains why you only have this Q equals 0 part of this first order diagram, because when you perform this impurity average, only Q equals 0 terms survive. Okay, so there is no finite Q contributions to the first order diagram. So that's the impurity average. And we will continue forming such a disorder average tomorrow and for the second term, and so on and so forth. And we will try to sum of all these Feynman diagrams up to the lowest leading order term, and then try to calculate self-energy contributions due to this impurity potential. So that's it for today.